Miami has reached 100 degrees exactly twice since 1895. The first time was in 1942. The second time was Tuesday afternoon. The reason it happened is not that the air over South Florida was unusually hot. A station in Oklahoma was 12 degrees hotter in the same air mass on the same day. It happened because the ocean breeze that shuts off Miami's heating every afternoon never showed up. By the end of this, you will understand exactly what failed and why forecasters are more worried about the mechanism than the record. On Tuesday afternoon, the official climate station for Miami, Florida recorded a high temperature of 100 degrees Fahrenheit. That is 37.8 degrees Celsius. It is a number that has appeared in that station's record exactly once before, and the last time it happened, the Second World War was still being fought. The reading tied Miami's all-time record high. Not the record for the date, not the record for August, not the record for the decade. The highest temperature ever measured in the city in a continuous climate record that begins in 1895. 131 years of daily observations. 2 occurrences of the number 100. The heat index that afternoon reached 107 degrees. A next weather alert was in force until 7 o'clock Tuesday evening. Local meteorologists reported the record that night, and health officials issued the guidance that always accompanies an event like this. Stay hydrated, limit outdoor time during peak heating, take frequent breaks in air conditioning, and check on children, pets, and elderly neighbors. That is the news, and on its own it would be a short story. A city tied a record. But the reason Miami reached 100 degrees on Tuesday is not the reason most people will assume, and once you understand the mechanism, this stops being a story about how hot it got and becomes a story about what stopped working. Miami did not reach 100 degrees because the air over South Florida was extraordinarily hot. By continental standards, it was not. On that same afternoon, in that same air mass, a weather station in Kingfisher, Oklahoma, recorded 112 degrees. 12 degrees hotter than Miami in the same sprawling dome of high pressure that was sitting over the southern half of the country. Miami reached 100 degrees because a protective process that shows up almost every summer afternoon simply did not arrive. The city has 2 defenses against triple-digit heat, and on Tuesday, the first of them failed. A wind from the wrong direction was all it took, and that heat has not ended. Yesterday brought heat advisories across the entire Florida peninsula except the Keys, with heat index values forecast between 105 and 112 degrees. Across the country, 72.5 million Americans were under heat alerts. What is happening in Florida is one visible edge of something much larger. The previous and only other 100-degree reading in Miami's history came on the 21st of July, 1942. The record stood untouched for 84 years. Consider what survived that record. The 1998 heat, the 2010 heat, the record-shattering summer of 2023, when Miami ran 46 consecutive days with a heat index above 100 degrees. Every one of those events came and went, and the thermometer never reached triple digits at the official station. 84 years of increasingly hot summers, and the number held. That fact tells you something important about how Miami's climate actually works, and it is the single most counterintuitive piece of this entire story. Miami has a global reputation as one of the hottest, most oppressive cities in the United States. Its all-time record high is 100 degrees. Florida's all-time state record is 109. Oklahoma's is 120. Minnesota is 115. A city whose name is practically shorthand for tropical heat has an all-time record that gets beaten by an ordinary summer afternoon in Phoenix, and Dallas, and Oklahoma City. That is not a mistake in the data. It is a direct consequence of the physics of where Miami sits. The city occupies a narrow peninsula with the Atlantic on one side and the Gulf on the other, water on 3 sides, and a daily atmospheric circulation that has capped its temperature curve for as long as anyone has been measuring. Reaching 100 degrees in Phoenix requires heat. Reaching 100 degrees in Miami requires heat and the simultaneous failure of the natural cooling machinery the city runs on. So when the number finally moved on Tuesday, the question worth asking was not whether the air mass was hotter than 1942. The question was which of Miami's defenses stopped working, and whether it is likely to stop working again. The mechanism that has held Miami's record in place for 131 years is the sea breeze, and it is worth taking a moment to explain properly, because it is not simply wind off the ocean. The sea breeze is what atmospheric scientists call a thermally direct circulation. It runs on a temperature difference, and it builds itself from scratch every single day. In the morning, the sun heats the land and the adjacent water at very different rates. Land has a low heat capacity. It warms quickly. Water has an enormous heat capacity and mixes vertically, so it warms slowly and barely changes temperature over the course of a day. By late morning, the air over the land is meaningfully warmer than the air sitting over the water a few miles offshore. Warm air is less dense, so the air column over the land expands and rises. That creates a small pressure deficit near the surface, and the cooler, denser marine air flows inland to fill it. The boundary between the two air masses is a miniature front. Forecasters call it the sea breeze front, and it pushes inland through the afternoon, often triggering the thunderstorms that give South Florida its reliable late-day downpours. Here is why that matters for the thermometer. When the sea breeze front passes a location, the temperature climb at that location stops. The heating engine is switched off, replaced by marine air that has been sitting over water, running in the low to mid-80s. In a typical Miami summer, that front arrives in the early to mid-afternoon, well before the day's theoretical maximum temperature could be reached. The city's daily high is not set by how much energy the sun delivers. It is set by what time the ocean shows up. That is the mechanism. It is dependable, it is physical, and it does not require anyone to do anything. It is also, as Tuesday demonstrated, conditional. The sea breeze depends on two things: the temperature contrast between land and water, and the background wind pattern it has to fight against. The temperature contrast was there on Tuesday. The background wind was not cooperating. Across South Florida on the 18th, a west wind was in place. That is an offshore flow, air moving from the interior of the peninsula out toward the Atlantic, the exact opposite direction the sea breeze needs to travel. When the larger scale wind is strong enough and pointed the wrong way, the sea breeze front cannot advance inland. It gets pinned at the coast, or held just offshore, or it never organizes at all. That is what happened. The circulation that terminates Miami's daily temperature climb did not develop, and with the break removed, the temperature climbed unchecked through the afternoon, until it hit a number the city had not seen since 1942. Notice what that means. Miami's record was not set by adding heat. It was set by subtracting a cooling process. The anomaly on Tuesday was not in the air mass, it was in the wind direction. A stalled upper-level ridge of high pressure anchored over the southwest and expanded east across the southeast coast had rearranged the surface flow across the peninsula, and the rearrangement was enough. That distinction matters more than it might sound, because it changes what you should be worried about. If Miami's record required an extraordinary air mass, then the record is protected by how rare extraordinary air masses are. If Miami's record only requires an ordinary hot day plus a west wind, then the record is protected by how rare west winds are on hot days. And that is a much less comfortable thing to be protected by. The open scientific question, and it is genuinely open, is whether sea breeze suppression days at Miami are becoming more common. If the ridge patterns that produce offshore flow over South Florida are shifting in frequency, then the mechanism that has held this record for 131 years becomes less reliable, and the record becomes easier to break than the warming trend alone would predict. Nobody has published a clean answer to that. It is the thing worth watching. Miami's second defense is the one that never fails, and it is the reason the city's all-time record looks so unimpressive next to Oklahoma's. The air over South Florida is extraordinarily humid. Humidity is not just a comfort problem, it is an energy problem. When sunlight hits a moist surface or a moist air column, a large fraction of that energy goes into evaporating water rather than raising the temperature of the air. Evaporation consumes energy. Every gram of water that changes phase from liquid to vapor absorbs roughly 540 calories, and that energy is no longer available to move a thermometer. That is why the hottest places in the United States are in the desert southwest and not in the humid southeast. Phoenix reaches 115 degrees because the air there has almost no water in it, so nearly all the incoming solar energy goes directly into sensible heat. Miami cannot do that. The energy budget gets spent on evaporation before the temperature can run away. Now here is the inversion, and it is the intellectual core of this story. The humidity that suppresses Miami's thermometer does not suppress the danger. It relocates it. All that water vapor ends up in the air, and the human body cools itself by evaporating sweat. When the air is already loaded with moisture, sweat evaporates slowly or not at all, and the body's primary cooling mechanism starts to fail. That is what the heat index measures, the combined physiological load of temperature and humidity. On Tuesday, Miami's air temperature was 100 degrees, and its heat index was 107. The lower thermometer reading described a more dangerous environment per degree than the higher reading did in Oklahoma. So Miami's low all-time record is not evidence of a mild climate. It is a measurement artifact of a dangerous one. The thermometer is not the instrument that tells you how bad it is in a place like this. It never was. The Kingfisher, Oklahoma reading of 112 degrees on Tuesday was a record high for the date, reported by the Oklahoma Messenet. Oklahoma City hit 109 the same day. Triple-digit heat extended across parts of Oklahoma, North Texas, and the Texas Gulf Coast. The 12-degree gap between Kingfisher and Miami is not a measure of how much hotter Oklahoma's air was. It is a measure of how much drier Oklahoma's air was. Same dome, same continental air mass, two very different moisture profiles. And the moisture is what decides how much of the sun's energy ends up as temperature versus how much ends up as water vapor. Oklahoma's higher number carried a smaller heat index premium. Miami's lower number carried a larger one. The Oklahoma City reading has its own oddity attached, and it is worth one beat. 109 degrees is not unprecedented there. It has happened 21 times in the city's recorded history. What is unprecedented is reaching 109 after the 11th of August. Every one of those previous 21 occurrences fell earlier in the season. By the third week of August, the sun angle has dropped, day length has shortened, and the theoretical ceiling on daily temperature is supposed to be coming down. It was not coming down. So the anomaly in Oklahoma is the calendar date rather than the value, and the anomaly in Miami is the wind direction rather than the air mass. Neither of these is a straightforward, it was really hot story. Both of them are stories about a pattern that is behaving in a way the season should have started to prevent. And that pattern is the thing actually driving all of this. The heat dome, a large stalled upper-level anticyclone, parked over the southwest and then expanded east. Under a ridge like that, air sinks. Sinking air warms by compression and suppresses cloud formation, which means more sunlight reaches the ground, which heats the surface further, which reinforces the ridge. It is a self-sustaining configuration, and it does not move until something with enough energy comes along to displace it. As of yesterday, 72.5 million Americans were under heat alerts. That is roughly 21% of the country. More than 40 million of them were assessed as being at direct risk from extreme heat. The core of the highest risk stretched from the lower Mississippi Valley across the Gulf states and into the Carolinas. Across large portions of the southeast, NOAA's HeatRisk product was flagging major, level 3 of 4, to extreme, level 4 of 4. The agency defines level 4 as, in its own words, a rare and persistent level of heat stress that poses a serious danger to anyone without adequate cooling or hydration, not to vulnerable populations, to anyone. The numbers coming out of Charleston, South Carolina illustrate what that means in practice. Charleston was forecast to hit 95 degrees today with a feels-like temperature of 108. Across a 5-day stretch, the city was projected to accumulate 21 hours of feels-like temperatures, ranging from 103 to 124 degrees. 21 hours. That is the cumulative exposure figure, and cumulative exposure is what actually drives heat illness. There's a second number in this event that gets less attention than it deserves, and it may be the most consequential one. Overnight lows across the affected region were expected to stay in the upper 70s. There is no meaningful nocturnal recovery in a pattern like that. Heat mortality is strongly associated with the absence of overnight cooling. The human body tolerates a hot afternoon reasonably well if the night that follows lets core temperature come back down. When it does not, when the low is 78 degrees and the humidity holds, the physiological load accumulates across days instead of resetting. A multi-day event with warm nights is a fundamentally different kind of danger than a hotter event with cool nights, even at a lower peak temperature. That is the shape of this one. And the storms that would normally break it are not going to. Afternoon convection inside the heat zone was explicitly forecast to provide little lasting relief. Ordinarily, a thunderstorm resets the surface temperature. A downdraft brings cooler air down, rain evaporates, the afternoon starts over. In this pattern, the storms were expected to add moisture to an already saturated boundary layer without breaking the ridge above them. Temperature down, dew point up, heat index up. The relief is on the thermometer and not in the body. While the southeast was locked under the ridge, the northern and western flanks of the same system were producing a widespread severe weather track, damaging winds, large hail, flash flooding, and isolated tornadoes running from the Ozarks through the Mid-South into the Midwest and along the East Coast. Those are not two separate weather stories. They are one system expressing itself in two different ways, and the connection is structural. A stalled upper ridge does not simply sit still. Its northern periphery becomes a fast, relatively straight west-to-east flow. Plains forecasters call this configuration the Ring of Fire, and along that boundary, clusters of thunderstorms repeatedly initiate and travel. Warm, unstable air on the ridge side, faster winds aloft along the rim, and a ready-made highway pointing east. The storms are not competing with the heat. They are being generated by its edge. You can trace that on the outlooks. Yesterday, the Storm Prediction Center carried a level 2 of 5 slight risk for the Ozarks and the mid-Mississippi Valley near Mayfield, Kentucky, and just east of Springfield, Missouri. inside a much larger Level 1 marginal risk stretching from New Mexico north into South Dakota and east into central Illinois. The primary hazard was damaging wind gusts, especially around and just south of St. Louis, with forecasters expecting the slight risk to expand north into central and northern Missouri and western Illinois as the afternoon developed. Worth noting for honesty, the HRRR model disagreed, showing little activity near Springfield or Cape Girardeau, a reminder that the guidance was not unanimous. Today, the track moves east. An isolated severe threat is in play this afternoon near Washington, D.C., Norfolk, and Philadelphia, built out of the remnant energy from yesterday's Ohio Valley and Mississippi Valley storms. The timing window runs roughly 2 o'clock to 8 o'clock Eastern, initiating near Baltimore, Philadelphia, and New York City, and pushing across the city and nearly all of New Jersey during the late afternoon and early evening, the rush hour window, before moving offshore. Wind gusts of 60 to 70 miles per hour are possible. Further west, a marginal risk runs from central Nebraska east to Minneapolis and western Wisconsin, with large hail the main concern and a low, disorganized tornado threat. Tomorrow is the day forecasters flagged as the most likely to produce a tornado of any in this stretch. A few supercells are possible from Marquette, Michigan south toward Chicago, with model guidance showing storms initiating near Janesville and Rockford and moving into the Chicago area around and just after the evening commute. Damaging winds remain the primary hazard, and the uncertainty on that forecast was explicitly conceded when it was issued. There is a slower variable underneath this entire pattern, and it is in the Pacific. For the week of the 10th through the 16th of August, the Niño 3.4 region, the stretch of equatorial Pacific used to define the state of El Niño, averaged 1.8 degrees Celsius above normal. That is 3.24 degrees Fahrenheit above average across an ocean basin, and it currently ranks as the second strongest reading on record for this point in the calendar. The only year that was stronger at this date was 1997. The event is still strengthening, and the forecast is remarkable. NOAA's Climate Prediction Center puts a 95% probability on this becoming a very strong, or super, El Niño during October through December. It puts a 69% probability on it, exceeding the strength of every El Niño on record going back to 1950. The forecast peak value for October through December is 2.66 degrees Celsius above average, a number larger than anything in 76 years of observation, including the 1982-83 event that currently holds the record. That is a record attempt in progress, not a completed one, and it deserves the honest caveat. 69% is not a certainty. The 31% branch, a very strong El Niño that falls short of the all-time record, is the single most likely alternative outcome, and it is not a small share of the probability. When we covered the typhoon that formed near the international date line and crossed 6,000 kilometers of open water to strike China earlier this month, the point was that the ocean state had already changed what storms were physically capable of doing. This is the same signal, further along. You can see it in the Pacific right now. Hurricane Lala formed on the 12th of August, strengthened into a hurricane on the 15th as it approached Hawaii's Big Island, weakened back to tropical storm strength as it interacted with the island's mountainous terrain, and then, after moving away from land, re-intensified into a Category 4 hurricane yesterday, with maximum sustained winds near 130 miles per hour. It is the first major hurricane of 2026 in the Central Pacific. A hurricane warning was in effect for the Papahanaumokuakea Marine National Monument from Lisiansky Island to Mauro Reef. That intensity trajectory, weakening over terrain, then rebuilding to a major hurricane, requires a reservoir of warm water and low wind shear that this part of the Pacific does not normally have. On the Big Island, the storm left more than 100 homes damaged or destroyed, 2 homes swept away by rainfall over Nalehu, up to 25 inches of rain possible at higher elevations, thousands without power, and 1 death. The National Guard and the Coast Guard were deployed for search and rescue. Meanwhile, the Atlantic, in the middle of what should be its active season, has been quiet. That contrast, a suppressed Atlantic and an unusually intense Central Pacific, is exactly what a strong El Niño produces. Through enhanced wind shear in one basin and reduced shear in the other, it is the cleanest available evidence that the ocean scale driver is already expressing itself. The first thing to watch is Miami itself, and it is testable within days. The forecast called for a pattern change later this week that would allow afternoon thunderstorms, including coastal storms, to return to South Florida. The question is which version of relief that turns out to be. If the pattern change restores the sea breeze, the daily cooling mechanism comes back and the temperature curve gets capped again the way it has been for 131 years. If it only adds moisture to a boundary layer that is already saturated, the thermometer falls while the heat index does not. Those two outcomes look very different on a thermometer and nearly identical on a human being. Watch the dew point, not the high temperature. The second thing to watch is tomorrow's severe weather. Forecasters identified it as the best chance of a tornado threat in this period, specifically near Chicago, while conceding substantial uncertainty. The Storm Prediction Center's Day 1 outlook tomorrow morning is the check on that call. The third thing to watch is the heat itself and the geography of the relief. There is a genuine cool down in the forecast for the end of the month across the Midwest, the Ohio Valley, and as far south as Tennessee, Mississippi, and Alabama. There is no relief for Texas and Oklahoma inside the 7-day window. The dome builds across the southern plains into Kansas through the weekend. Any framing that presents this pattern as breaking would be wrong. It is shifting its center of gravity, and it is not shifting off the people who have had it longest. The fourth thing, and the one with the longest reach, is the next monthly ENSO update from the Climate Prediction Center. Whether the Niño 3.4 index stays on the trajectory toward that forecast October to December peak, and whether the 69% probability of an all-time record event holds or falls, is the single most consequential number in this entire story, because it determines whether the coming winter has any historical analog at all, and underneath all of it is the finding that should stay with you longest. Miami's all-time record is low because the city is protected, not because the city is mild. Coastal cities are defended by processes. A breeze that arrives every afternoon, a night that cools, a storm that resets the surface. Those processes are not guarantees. On Tuesday, one of them did not show up, and the city recorded a number it had not seen in 84 years. The trend data says the margin is thinning. Miami now runs 44 more above normal days each summer than it did in the 1970s. Its June through August average has warmed by 2.6 degrees Fahrenheit. Its annual count of dangerously humid heat days has gone from 50 in the 1970s to 117 in the last decade, with researchers attributing 80 of those days to human-caused warming. The record needed a west wind to fall. The question that remains open is how much of a west wind it will need next time. We will be tracking this as it develops.